All right. Many thanks to you all for joining today's Space Syntax Lab seminars. I'm really excited to welcome Dr. Yao Shen today. He will talk about functional visibility graph analysis, quantifying visuofunctional space with social media check-in data. This is quite interesting data that has interesting research that has recently been published in Environmental Planning B, for those that are interested. And it connects kind of VGA analysis with functional urban space. Dr. Yao Shen is an associate professor in urban analytics at the Tongji University, director of the Center for Urban Science and Planning for the Ministry of Education of China, and an honorary fellow at the Center for Advanced Spatial Analysis here at UCL. In addition, he's the associate editor for the SAGE journal, Transaction in Urban Data, Science and Technology. Yao obtained his PhD from the Space Syntax Lab and then worked as a research associate at CASA before he joined Tongji University. His research interest covers spatial analytics, urban modeling, complex networks, data science, urban geometry, visualization, and urban planning. He was elected for the Shanghai Rising Star program in 2021 and the Puyang program in 2018. So we welcome a real expert in the field. And before we start, I should mention we will have a Q&A at the very end. So if you have any questions during the talk, please put them in the chat so we can get back to them at the very end. And with this, Yao, the floor is yours.
Right. Thanks, Kimo. And thanks to all old and new friends. And hello, everyone. And as I introduced by Kimo, I'm now the associate professor at Tongji. And I was the alumni from Space Syntax Lab. And for my PhD 10 years ago with Kevin and Aurora. Well, I was surprised because this event was very departmental and was very internal. And I joined this series 10 years ago. It's in 2012 when I was a PhD student. And it's pretty much like a 10 years kind of a review of my work, of my recent progress. And he also kind of thinks, and there's lots of my supervisors here, and Kevin, Aurora, and Mike, and they're all my PhD and postdoc and supervisors. So it is pretty much like 10 years, another kind of upgrade from something to kind of a new level. Hopefully, I can make you all satisfied. So very happy to have a chance to talk to all of you here. And today I will talk about a small piece of my work in space syntax. And the reason why I say this small piece because it is only kind of an article, but this belongs to relatively larger work which I have conducted for my PhD, which is try to combine the emerging urban big data, spatial temporal data in particular, and with the spatial network analysis. So this is a work, this is recently published in EPB, and this is about extending the VGA with emerging so-called big data. Let me start with some research background. Instead of reviewing all the relative work, I assume that most of you, today's audience have known VGA quite well. And so this background is more like a kind of motivation. And nowadays we are currently facing something we call a shift of data environments, from the classic one to the new one. So, and the left one is I mean, it's normally featured by the data as ways the low frequency aggregate data or the spatially sensed data. And in fact, we can easily recognize that basically we use the spatial layouts before, and assuming that they can be overlapped for design purpose. And this kind of structures is relatively easy to be understood, easy to be used, and easy to be shared within the design or the spatial intervention process, because everybody can note the tree-like structure. But now we are dealing with the timeline, social networks, various contexts that are all embedded in spatial layouts. They are interconnected in relatively complex manner. And Mike called this high frequency cities. I treat this kind of data environment as the kind of the features of the high frequency city, because the new data sets is a very high frequency and disaggregate across people and resources or behaviors. And this is now called social sent data, because people understand to be a new census, and the data set from the data from the people and creates a kind of a new sensing technology, or a sensing approach. We can call it social spatial sensing. So, and in fact, it's an increasing complex of the new data environment. It is not a kind of task for space syntax only, but this is a global kind of challenges for the whole community of spatial analysis. So, and the shifting data sets are now leading to a shifted focus from the estimating the flows to a kind of having flows in hands, or something we call digital twins, and with the real streaming data set. This addressed the question about the significance of urban models. We used to estimate urban performance before. And I would say space syntax is a very good urban models before, using relatively simple, straightforward networks, spatial networks, to approach or to model the kind of relatively complex urban performance phenomena. But now we have a way to map the performance directly, or map the flows directly. Sometimes it could be hourly based or even minutes based. So what is the new model in the data environment with new data? How the emergence of the urban big data can benefit and the evolution of a space syntax model. Sorry. Well, in the past several years, we published several studies to try to incorporate the space syntax model with urban big data. And here is a kind of basic maps of about what we have done. These kind of actions enable space syntax research move forwards to a relatively high frequency perspective, as Mark has mentioned. And that is kind of enabled by those fine scale spatial temporal data with the relatively static urban network data. We have proposed some methods to do this with two typical type of data. The first one is the location-based service data, we call it LBS. That is quite point-based. And the other one is the kind of a trajectory data. This is polyline-based, if you like, or the point data in a various space and times sequence. For instance, we will introduce and briefly about what we have done in here is that the first one is the urban function connectivity, we call it UFC, and the PCI, the physical capacitance intensity. And this kind of two methods is just push the conventional space syntax models into a relatively high frequency way. And we use the LBS data at urban scales to use to develop a kind of urban function connectivity measures. And then we use the structured data to make this more dynamic and to in a kind of model we call the PCI. And today we will introduce the model that we just put in the UFC to find a scale into a visibility analysis that we call the functional visibility graph analysis. And let me just briefly introduce what we have done with the so-called urban functional connectivity work. It was published in 2016. This is and that is a work that we used. We proposed a new measure called UFC, which measures the centrality featured by the street network and checking urban activities too. But this is along with relatively big urban networks. It combines the density and the aggregation of the activities, diversity, the complementary effects between those kind of activities, and the so-called the delivery efficiency featured by the mean angular change along the shortest path. So the UFC, it just combines all these three. It shows the centrality features by the function and land use or kind of attractions, if you like, in the streets, in the street network, which is fully different we have found by the spatial centrality only. We also test the contribution of these introduced measures. We find that they can augment our prediction about housing prices, basically, particularly at a very local scale. So though it does not kill space and text indices, we want to say that we see the newly emergent data, if they can be computed properly, and they can augment the spatial network analysis for predicting the socioeconomic performance. Well, I want to add a new point here is that most of you might know that in history, there's other tools that can also deal with the kinds of attractions, so-called attractions. For example, place syntax tools that can deal with the buildings too. But what I want to mention here is that that kind of data set is relatively static because the building is relatively static. And now we use the checking behavior data set. This is relatively fully new. And this has reflected the popularity of the place and the people engagement within the press. So, and the other works I want to mention is that combine the special text model with the point and with the structured data. And here we just make a kind of very over space and text, if you like. So here we mention the likelihood of any two people can see each other face to face in each street by combining the kind of structured data sets, fine scale structured data sets along street and with the spatial networks. You can see the brace of the centrality, if you like, from the morning to the evening. And in the evening, the centers tend to be strength and tend to be relatively small size. And it tends to be very, very dispersed during the morning peaks. And so we call this the kind of an area over space and text. Of course, if we have a data of kind of fine scale data along on the time dimensions, we can imagine that we can have every minute space and text too. And here, in every hour space and text, we find that cities have a different typical centrality performance, which is differentiated across time. In the case in this slide, you can see how urban networks is activated by people's daily movement. And in turn, these results are quite sensitive to the change of spatial layout. That means when you change the spatial layout, but hold the people's preference constant, and the future flows change accordingly. Based on the measures we have developed, we also kind of try to dig more. So we use data science and technology. We can dig more information out here. And we also did, here's an example that we detected typology of urban streets according to their roles in facilitating people's face-to-face encounter in space. So you can see some of the streets are very kind of pretty much like the neighbors, right? And some of them are kind of 24 hours active areas. So this in fact challenges our conventional thoughts about how local community emerges. Here, community is not the longer static concept, only defined by space, but very dynamic one. The boundary of this community is very sensitive to the interaction between spatial layout and how people use it. That means for any kind of a community, even though the spatial layout never changed, the people live there changed, this behavior habit and the kind of behavioral habits changed. The definition of this community will change accordingly. So we recognize that huge potential of combining space and text model with newly emerged data. For my today's research, my motivation is to think about the VGA with functional data. Let me discuss this a bit first. We read space by not only by reading space, but reading how other people use space too. So like image and like this kind of image has illustrated, we as a human being, we detect what kind of activities other people are doing, evolving, and we can further detect where they went according to some features. For example, shopping bags, we can basically now and recognize that where they have gone. So visibility to activities are also very, very important for the high dense environment. So we will do here. We will deal with three very basic questions: how to measure a visual functional landscape properly, and to what extent does FVGA that we so-called can augment the model for predicting urban flows, and then what can FVGA uncover beyond the conventional VGA studies. So let me just introduce the FVG briefly. So as you can see in these three diagrams, and the figure A is a very typical VGA model, which is we assume that every space is the destination for people's movement, but this is not real all the time, right? We move in the city, we have very particularly destinations, which is pointed out by the geographers as the kind of attractions. So assuming that when we add the kind of new attractions within this space, and everybody should make this as the destination, the visibility to this kind of functions is tend to be quite different from what we can use what we recognize in the conventional VGA model. And if we just add another one, and we will recognize that the overlapped area of the isovis for and the individual attractors, they tend to be relatively more popular area because it's a kind of a relatively direct visibility to these two attractions. So if we have this kind of different map, we just add kind of the functional node and as a new node and for the VGA analysis, then we can enable a kind of an analysis for computing the kind of visibility to different kind of functions. So in a T-shaped model, the distribution of the mean visibility steps to the space can highlight a different kind of area. They have a different kind of shallowness to different kind of for different kind of space. So this ratio shallowness to attractive destination is just a kind of also reflect the effects of functional distribution on people's perceptions, which is also essential for evaluating land use allocation in the spatial context and where they will be implemented. So here's a kind of frameworks for conducting all this. We use different colors to represent the different schemes. So the light green is just the basic data. We only need the point of interest, which is showing if this is the destination for people. And we use social media check-ins to represent the kind of popularity of these POIs. And then we also need a kind of spatial layouts. This is we only use for conventional space syntax and research. But we also need the gate counts. It's not only for the calibrating the kind of very kind of effective radius or effective cell size. Otherwise, we cannot recognize that which kind of radius could be the more effective one for the future for discussing a certain type of performance. So we use the gate counts to validate those kind of model too. And we just translate the POI to function nodes. And we use the spatial layout to turn out the spatial nodes. And we just build up the visibility edges between function nodes to all the spatial nodes. And then we have the functional visibility graph. By defining the radius we want to address, we can compute a different kind of conducted graph analysis. We have three basic measures, which we call the function size, entropy, and the mean shortest path depths. And then we will have a second layer of these measures, which kind of reflecting the interplay between these three basic measures that we call visible functional connectivity and the visibility and the functional closeness. And this kind of relatively composing measures can be used to address the narrative of the visibility and to map the visibility function centrality and to detect the visibility function region. Well, I will skip a bit of the details. You can read more on the papers, and I will give you relatively clear and precise definition in mathematical way. But here, I just want to give you a very brief idea of what this measures will address. The first one, the visible function size, is kind of measures how many activities could be seen, and functional entropy or the evenness. This is about how mixed the visible activities are, and the mean shortest angular depth past depths. This is how visibly close those activities are. So this is a very basic 3 elements, and we follow the Turner's works. It's about normalizing and the kind of the angular the mean distance. The reason why we do this because we test a different kind of way to normalize them and then to aggregate them. We want to point out the risk here is that if you use a different kind of procedures here, you will get different formats of the mean depths, which will hugely impact the final results. After conducting different experiments, we find that we have to normalize them first, and Turner's work can help us to do that. And then we will develop some kind of interactions. So interaction among these 3 basic dimensions and are documented in these 3 measures. The first one, we call it the connectivity, because it's, well, you may recognize that we use something new name because this is not always the case, because originally I would use relatively the name they're quite similar to space syntax, but sometimes the reviewer, if they from computer science backgrounds or other kind of backgrounds, they will ask you to use relatively well-known or widely used measures. So here, and the visual functional connectivity, in fact, this is the iso-based. But here, we have to use the kind of connectivity because this is a very initial ideas in complex network science. And this is also kind of a suggestion from the reviewer. And then, we will have the functional visibility. And we will discuss this in very end in the discussion. I will show you why we think about the interplay between the size, entropy, and the mean depths in this way. It is pretty much like the integration measures in space syntax, to be honest. So this is the integrated visible centrality. And then we will have a visible function closeness to different given type of activities. And this is makes the measures to multi-type. This is very sensitive to how we divide the urban functions to different types. You may recognize that if you just compute the entropy, and the key thing is that how you group the land use. If you group the land use in numbers, rows and groups, is a very large number of groups, and the entropy will change. So the entropy is a kind of way, it's kind of an indices that are quite sensitive to how you group the kind of the land use. So for detecting the kind of urban regions, we use the methods we call it in consensus clustering. This kind of a methods can enable that we use the original functional visibility graph for different type of land use. It can make the visibility graph to a multi-layers, if you like. And this kind of a multi-layer or multi-dimension VG can be clustered as a one. So this is consensus clustering can help us to do that. And the other kind of reason for using this kind of clustering, network-based clustering technology, because in the other kind of way, for example, the k-means, and you have to decide a case, but this is there's no kind of a very good kind of indice that to decide which k is the best. So here we just make this kind of problems turn into a network problems. We use the kind of community detection to do the kind of detection. Then we will use the modularity to quantify the significance of these regions. If the modularity is larger, that means that this community is more significant, and this is more likely to happen. Okay, so the data we use is quite very and it is the data sets with the, as I have mentioned, and this is a POI with the check-ins. So the basic data set we here is that the street networks as shown on the left, and the check-in behavior data set here, we just assign the number of check-ins to individual POIs. So each POI is not representing a building, but representing that kind of functions that are reported by the map users. And we just remove this is all the kind of fake points. The fake points including the one that's the users has reported the functions, but not exactly the same when we do the geo coding task. And the other kind of thing is that we just remove all the functions that's no one check-in. And then we have the kind of the gate count, because we want to validate that if our methods can be more is more effective or is effective. So we have to use the gate counts to calibrate or to validate the effectiveness of our methods, and also to calibrate the optimized radius. So we also test the kind of whether the kind of the data we used is representative. The kind of advantage of the big data is that you can get a very fine resolution, and this is give you more spatial temporal information. But the bad thing is that it might have some bias. So the one way we use to validate this data, we just test and compare with other kind of studies if they follow the same checking behavior laws that is widely shared by different kind of cities. And we also test the kind of how to group the kind of land use. Here we recognize that we must use a way to recognize the meaningful groups of land use and list. In fact, essentially, we have more than 300 type of functions from the original data. And we just test that if they can be grouped to one groups. And we just test the sensitivity with the entropy. And we recognize that 11 main groups will be a good kind of definitions for Tianjin cities. We also recognize that for Shanghai or for other kind of cities, different citizens who live in different cities, they have a different kind of culture to use in space. For example, in Shanghai, and relatively international, and people will have a more recreational activities, but in Tianjin, there's relatively fewer people use that kind of activities. So we just have a kind of data and clustering methods to dig the information out. And 11 groups is this 11 groups and definition is used in our work. So let me just give you introduce about the results. This is the very first one. We have to calibrate and validate and the results. So here we just done a very kind of a simple task as normally space and text research have been done. And we just try to correlate the method the centrality methods we have with the observed movement patterns, the gate count data. So you can recognize that the first one information is that most of the basic FVGA indices, as I have shown within the red box, that's the basic FVGA indices are statistically significant to describe the movement distribution, and they overweight the classical VGA indices. And you will recognize that most of them are relatively statistical significance, and they will have a relatively higher adjusted R square. And we also recognize that the functional visibility in that, which is to combine the three basic one, achieves the highest predictability on the movement distribution. This is suggests that the interaction among these three basic indices is sound for flow estimation. Otherwise, we cannot say that the way we just combine them is the correct one. And this trend is more significant when the radius is fixed around 300 meters, in which a functional visibility can describe more than 75% variation of the human flows. So we pick 300 meters as the kind of optimized radius for estimating and the kind of the patterns, the flow patterns. We also kind of to calibrate the independent contribution that each index makes. So we use a series of OLS models and to validate their contribution. So model 1 and model 2 are distinctive for using FVGA variables without or with tracking informations. We want to calibrate if we need the tracking information, or we just need the POI only. And then the model 3, we use both. So the first one information we can get here is the measurements in the FVGA models at the pedestrian scale 300 meters are all significant, whereas the measures at a 0 and or at infinite radius and Rn, and they are reported to be non-significant when in the model 3. So this confirmed that the checking data sets contributes to having relatively better predictability of the flows. It confirms the necessity to use the checkings informations. If you do not use the checking information, the model is will lose nearly 20% exponential power. And the measures with weights from the checking records outperforms the ones without them as significant variables in model 3. This is yearning that the adequacy of using the social media checking data is a function of attractiveness. And this kind of remarks demonstrate the effectiveness of the proposed measures and the suitability of the required data set for modeling flow aggregation and people's perception in this area. So we recognize that we're using the indices that we proposed with the checking informations, and we will increase 20% predictability. And we will recognize that in model 1, those significant ones tend to be non-significant. That means that they are kind of better to buy and the indices that we proposed. And you might be curious about that, of course, you have a land use data, you may have a kind of better predictability, but is it universal for the whole cities? Particularly for those areas has relatively less number of functions. We'll just do the test because this is a label for as well. We cannot have a very fine scale pedestrian flow data. So we're just using 20 windows for 1 kilometer 1 kilometer square to test whether this model can work. We recognize that for 20 windows that we select, and this is randomly selected, in fact, and there are only 3 FVGA performs better. VGA performs better, and for most of them, FVGA performs better. And more clearly, if a window, 1 kilometer, 1 kilometer by 1 kilometer square, if this kind of a square, within a square, there are more than 8 functional nodes, functional informations, the model can work. And for using this kind of model, we can use this to better understanding the environments. And this is the work, in fact, proposed by Mike, and in his works in 2003, it is also published in EPB. And he just proposed a method as we have a kind of routes within these sites, and then we just kind of record this kind of and performance of different kind of VGA information, then we have a kind of idea of the performance of these routes. This routes could be any kind of routes you want to design. And so in this kind of figures, it shows a variety of spatial experience ranging from straight to squares, which complex regions of various accomplishments within public space. This shifting experience along such a lens can be logged as by outlining the change of visibility profiles from the beginning to the end. So this has a potential for evaluating the performance of sequence of place as a chain that facilitates a fascinating tool as expected or not. So you can recognize here. In fact, when I select this area, I forgot to mention because there's one challenge of using VGA within the urban environment is that the boundary effects. And this is not true for the architecture research because basically for the architecture space, the space is closed. So you normally don't have that kind of boundary effects. But for urban research, how you select the boundary will hugely impact the results. What we want to say here is that if you have a land use information, it can largely reduce the uncertainty of the boundary effects because the land use information is a kind of mediates information between the space and the people's behavior. It could kind of it can kind of correct a bit of the models. So here we just map the distribution of various meshes at the absolute radius and calibrated pedestrian radius. At the radius with no angular change. The main street in this area are highlighted by the different visibility information. The Binjiang Road, which is highlighted on the top left with the red color, manifest with the high levels of visible functional connectivity, and with other kind of the roads quite near to it and class features by the high levels of visible functional entropy as shown in the figure B. And the intersections between those main roads, incorporating the density and diversity of information, are captured as the spatial with a higher level of immediate and functional visibility than other places, as shown in the figure C. By contrast, the geometrical center of this area is scored highly with respect to the global functional visibility measures. So as shown in the figure D. So at 300 meters, the pedestrian distance ratio that we calibrate, the Binjiang Road and its the kind of and its interlocking streets are the most visible places exposed to activities with high scores of function size and entropy, but low value of mean shortest angular per steps. This result shows that the multi-scale nature of the visibility landscape and the potential of these measures as a series of visual centrality to estimate urban flows and other movement-related urban performance. And we also, and this is the result that we use the consensus clustering, and we recognize that and we can find that there's a visual community within the kind of a certain fine scale, certain area. And there are 7 clusters are detected for these time sections. Cluster 1 and cluster 7 are those the business area dominated by retail and recreation activities, while they can be easily distinguished by the clustering of hotels and catering activities. Cluster 3 is also an active area and characteristics by transport nodes, parks, culture sites, and hospitals. They're more visually perceived than other places. Cluster 4 is less active than cluster 3, indicated by the lower level of functional visibility closeness, though it can be featured by the clustering of similar activities in cluster 3. 5 and 6 are both highlighted by the higher visibility to education than to others, but the former can be further captured as this visual exposure to the transport-related service, and the latter can be featured by its visibility connectivity to hospital and public service providers. So this portion of space is validated statistically by a maximized modularity score, which is 0.373, which is a very good score. So that means that they have a kind of a densification of a certain type of land use for our visual scape. So the boundaries of these functional regions are consistent to people's perceptions. For example, cluster 3 covers the areas where the entrance of a very famous high school in China is open to. And a city has a city bus terminal is located in cluster 4, and this is visually exposed to cluster 3. And it is recognized that the functional visibility scores for the study area grow from 2010 to 2014 with increased visibility functional size entropy and decreased angular step depths. So it can be recognized by the cumulative variability graph. This showcases a tendency that the functional visibility information was enriched due to the agglomeration of urban functions where the spatial form is static. I have to mention it here is that we selected this area because this is a historical area. The spatial layout never changed in the past 10 years due to the policy. So it provides a kind of idea environments for why FVGA can perform better, because the land use is continuously changing here. The clustering of urban functions maximize the interconnectivity by reducing the visual cost between them within this kind of process. And this is also demonstrated by the results of functional ability in 2010s and the cumulative probability curve of the proposed measures as shown on the right. So you can compare the kind of centrality and the visibility results for 2010 and 2014. You will recognize that the densification and the diversification of this whole area for our visual landscape. And this is the kind of the functional region detected in 2010, it's 4 years ago, as I have 2 years ago for the time section that we have selected for analysis. So this is the modularity here is 0.75. That means that the densification of urban land use for the visual landscape is more significant than before. And it's also gives you a sense that how different kind of the functional distributions within the visual landscape change rapidly. Well, if you look at this kind of areas, functional structures, you can recognize that some of them just split to 2 groups, and some of them just extend towards the street. So it means that the kind of market logic that the land use have their kind of a micro and economic or diseconomic process happens within the visual area, which is also created kind of a configuration, if you like. So for the very end, I just want to firstly discuss as a kind of what we have done. First of all, this is a methodological work. We want to add a kind of emergent and checking behavior data sets with VGA and to quantify the visibility to various activities based on the spatial and functional configuration sensed by the LBS and the check-ins. So, and the effectiveness of the proposed metrics has been validated. The improved performance of the models with all the kind of proposed factors indicates the importance of the functions in shaping our visual landscape, in which in turn the shaping traveling patterns. The contribution of the tag, the POI on the check-ins is confirmed by the advancements of the model fittings against the gate count. And by calibrating the optimized radius 3 meters, and the measures can also tell us about a point-based perspective about the centrality rule-based scope showing about along the path selected for showing the spatial narrative, and area-based scope showing the sense of the place based on the typology of the function that we call the functional regions as proposed. So then the kind of this kind of analysis can be redo within shorter term by using the updated data. So we call this is a high frequency information analysis of the spatial configuration, which is enabled by the new data environments. And for the very end, for the discussion here, I just wanted to give you three messages, which is something that I feel that's quite important when I conducting this research. The first one is that we try to bridging the geographic and the geometric accessibility. I just want to represent this works as a kind of equations. Mike might know this quite well. And the geometric accessibility as a kind of indicated by the integration methods, basically as shown on the left, is the knot count subdivided by mean depth, basically. Which is also kind of logic of the size divided by the mean distance. For the geographical accessibility, basically, and the accessibility also kind of with the kind of the size of the reachable activities or the functions subdivided by, or we use the kind of negative power functions. So here we use the kind of distant decays, the firms. So the distant decay firm is quite like then you just subdivided the size by the kind of distance. So we want to place our FVGA accessibility in the middle, which is combine the size, the entropy. We use the entropy as the punishment of the size, because when you think about the urban functions, they have a quality effect. That the quality effects that means what kind of functions are combined. They have a kind of interrelationships. For the people, what kind of people will address? So we have a kind of a quality effect. So we use this as the power. We use this as the as in a power firm, is that it's given a kind of it makes possible that we distinguish that S equal to 0 or E equal to 0. And you can recognize that the only thing here is that the definition of the distance is quite essential firms within our methods. We recognize that this is a very fundamental things when we have a logic of the whole urban space. We try to bridge the geometrical urban space with the geographical urban space. We think about that the urban design or the urban planning or the regional planning or at different kind of scales. When we have the frequency change, we basically have the kind of and everything changed accordingly. For example, when the frequency is very high, we normally focusing on the high resolution or micro scale things. Of course, when we're focusing on micro scale things, we were focusing on people or relatively small scale agents, if you like. And if we focusing on the geographical space, we're basically using the polygon or the green cell fishnet or the blocks or something like that. And that is for analysis in the regional problems, because people use this to do the spatial statistic of population or economic indices. So we think that when we try the frequency, research frequency, we will change the record and the resolution, scale, what kind of elements we're focusing on. But of course, we change the kind of the distance definition. In our work, we find that space syntax is a kind of an essential of space syntax is for defining the space, defining the distance as the cognitive distance, and in the angular ways or in the topological or other kind of topology way formats. And the third message here is that we want to say, I just kind of unfold a bit of the natural movement models. I would say a natural movement model is established model that is give us a sense that how space will impact the land use. But in turn, my work is not kind of new things for space syntax, but this is something that we unfold, that we call it the multiplayer effects. If we just unfold this kind of effects, we will have a kind of high frequency things. We must add a kind of urban functional centrality within that. And that is why I think that we are not a kind of destroying a space syntax. We're just extending into a relatively high frequency scope. And this high frequency scope has been well proposed by Mike, is also by Bill Hillier in the natural movement, because we have a kind of elements of the multiplier effects. And that is why we think that the urban functions is also kind of essential type of urban configuration. If we just put it precise, or put it precisely, I will say the urban function is a high frequency urban configuration. So this is basically my today's talk. I hope that you can enjoy it. And there's some more relative work. If you have time or you have interest, you can read that. They were definitely better than my representation, because I just, this is very late in China. Okay. Thanks, everyone.